Hello, this is Satbir. The topic of our discussion in this video tutorial is pointwise convergence of a sequence of functions. So I will start this video tutorial from the formal definition of pointwise convergence. For the definition, let we have a sequence fn of x which is defined on a set A to R. This will be a sequence of function. Then we say this sequence f n's of x, this sequence of function converges to its limit f of x on the set A if and only if for every epsilon positive and a fix x belongs to A, we can find a capital N. This time this capital N can depend on x and epsilon, and this capital N is a natural number. And so that how we want to find, so that the distance between the sequence and its limit must be less than epsilon, this given number epsilon, when n is bigger than or is equal to capital N. So when we take the n bigger than or is equal to capital N, the distance between the sequence and its limit must be less than epsilon. In that case, we say that this sequence f n of x converges to its limit f of x pointwise. Next, I will show you the example of pointwise convergent. For this examples, I consider the sequence of function f n's of x is equal to x square plus nx whole thing is divided by n, and I will prove this sequence is converges to a function f of x which is defined as x on that set R. And I will prove this pointwise convergence by using the definition. So if you want to use the definition to prove the pointwise convergence, first we need to do some scratch work. So scratch work is, we would like to show that the distance between the sequence and its limit must be epsilon, and this happens when I choose my n bigger than some capital N. So, and this capital N I need to find. So first we will start computing this distance x square nx whole thing is a divide by n minus x. So we'll make the same denominator and we'll subtract these two terms. This will be minus x. So don't forget the absolute value. I can remove the absolute value from the denominator because n is a positive, and this cancel out, and x square is also positive, so I can remove the absolute value from the top as well. So now as you can see that if I choose my n bigger than x square over epsilon, then I can make this quantity less than epsilon. So this gives me the choice of my capital N. So I can choose my capital N as the greatest integer function of x square divided by epsilon, and I will add 1 to make sure that this inequality hold. Now I will write down the formal proof. So for the proof, first we will choose the epsilon positive, and also we will fix x which is belong to the set of real, and then we choose the capital N. So capital N, the choice of capital N is x square divided by epsilon plus 1, and then so that when n is bigger than or equal to capital N, we have, so as you can see, that if I choose my little n bigger than capital N, then the distance between f n's of x minus f of x, this will be eventually is equal to x square over n, but n is bigger than or capital N, and the capital N is defined as the greatest integer of x square over epsilon plus 1. So definitely this will be less than epsilon when I take n is bigger than or is equal to that capital N. And this proves the pointwise convergence. So this implies this sequence f of xn converges to f of x pointwise. Now let's take one more example of the pointwise convergence. In this example, I consider my sequence of function as nx whole thing is divided by 1 plus nx square, and I will prove that the sequence of function converges to the limit 1 over x when x is not equal to 0, and if x is equal to 0, then it is converges to 0. So let's prove. So in order to prove, again we first have to basically do some scratch work. So as you can see that here we have to consider the two different cases when x is 0 and when x is not equal to 0. So x is equal to 0 is an easy case, but we need to prove in this case that f of n of 0 and minus 0, this distance we need to make less than epsilon, or another word, we need to find n so that this distance is less than epsilon when I take my little n bigger than that at capital N. In this case, as you can see that if I plug 0 in my sequence of function, then I will get 0. So 0 minus 0, this is basically 0, and you can make this less than epsilon even if you choose capital N as 1. So for this is a true for all n. So if you take your capital N, so this will be true when little n is bigger than capital N. Now let's consider the second case when x is not equal to 0. So what we need to do is we need to find a capital N so that when I take my little n bigger than that capital N, the distance between nx 1 plus nx square minus 1 over x is less than epsilon. So let's do some simplification to this term. So it's gonna be x 1 plus nx square, the absolute value of this term, and this is going to be nx square minus 1 minus nx square of absolute value. This term will cancel out, and if you simplify the top and bottom, you're gonna get 1 because the absolute value of negative 1 is just 1. So this is the absolute value of x. This is a 1 plus n x square. And you can make this less than 1 over absolute value of x n x square. And this is a simply is equal to 1 over n x to the power cube. Absolute value of x to the power 3. And I can make this less than epsilon if I choose my little n bigger than epsilon x to the power 3. So now this gives me the choice of capital N. I can choose my capital N x to the power 3 divided by epsilon plus 1. So as you can see that if x is equal to 0, n is automatically gives you 1. So this will even cover the case when x is equal to 0. So now let's write down the proof. So for epsilon positive and x belongs to the set of reals, we choose, if we choose capital N as absolute value of x to the power 3 divide by epsilon plus 1, then the distance between f n's of x minus f of x, which is this function, this distance will be less than epsilon when I choose n little n bigger than or equal to capital N. And that calculation is follow from here. Even if you consider the two different cases, you can make this distance less than epsilon when you choose your n bigger than or is equal to capital N. And this implies f n's of x, this is a converges to f of x pointwise. And this complete the proof of this example. Here I have one more quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. This is also the end of this video. Thank you very much for watching. I will see you in the next video. Bye for now.